You wake up in the morning and place your feet on the floor. You take a few steps across the room, reach for a chair, and sit down. Nothing about the experience feels strange. The chair supports you. The floor pushes back against your feet. Your hand can press against the wooden armrest and feel its resistance. If you knock on the surface, you hear a solid sound. If you try to push your hand through it, the chair refuses. As far as your senses are concerned, this is what solid means. Something is there. Something occupies space. Something stops you from moving through it. And you have trusted that experience your entire life. But look more closely. The chair beneath you is made of atoms. Your hand is made of atoms. Your bones, your skin, the floor beneath your feet, even the air moving through your lungs, all come from the same microscopic world. And at that scale, the picture becomes profoundly different. An atom is not a tiny hard marble packed completely full of material. Most of its structure is the vast region between its extremely small nucleus and the surrounding quantum description of its electrons. So when you sit in that chair, you are not simply encountering tiny pieces of matter packed together like miniature billiard balls. You are experiencing something much stranger. Your body feels solid. The chair feels solid. The floor feels solid. Yet the microscopic structure responsible for that solidity does not resemble the solid objects your senses have taught you to imagine. And this is not some exotic phenomenon happening in a laboratory. Your own body is participating in it right now. Every step you take, every surface you touch, every breath you inhale is governed by this hidden microscopic structure. The ordinary world has been giving you the evidence your entire life. You just had to look closely enough to notice. And once you realize that the floor beneath your feet is built this way, the obvious question becomes impossible to ignore. What exactly is stopping all of those atoms from simply passing through one another? If an atom is mostly empty space, then something about this picture seems impossible. You reach out and place your hand against a table. You cannot move your hand through it. You lean against a wall. The wall pushes back. You sit in a chair. You do not slowly sink through the seat and disappear into the floor. So what is actually stopping you? It is tempting to imagine that atoms are simply tiny, solid balls packed tightly together. But that picture breaks down immediately. The nucleus does not fill the atom either. It is extraordinarily small compared with the overall scale of the atom. And saying, the particles repel each other, doesn't really solve the mystery. Repel how? Why? What produces the resistance you feel when your hand presses against a table? And why does that resistance appear so reliably in every ordinary object around you? Look around your kitchen cabinet. A glass, a ceramic plate, a metal spoon, a wooden handle. Different materials, different structures, different atoms, and yet your hand encounters all of them as solid. Your phone does the same thing. So do your glasses. So do your bones. The same microscopic rules are operating underneath all of them. This is where the familiar phrase, atoms are mostly empty space, becomes dangerously incomplete. The phrase is not entirely wrong, but by itself, it explains almost nothing about why matter behaves the way it does. And this is the part that often gets skipped. You are usually given the slogan, shown a picture of a tiny nucleus surrounded by a huge amount of space, and then left to assume that solidity somehow emerges from the pieces simply being there. But the interesting physics is what happens next. Because the reason your hand cannot pass through a table is not hiding somewhere inside a mysterious property called solidity. It comes from the rules governing matter at the microscopic level. And before we go any further, there is something I need to clear away, because this subject has been simplified so many times that the popular explanation is now often more confusing than helpful. You have probably heard the sentence before, atoms are 99.999% empty space. It sounds powerful. It sounds like the kind of fact that suddenly explains everything about reality. And this is where I want to slow down, because the slogan contains an interesting intuition, but the explanation that often follows it is incomplete. You will sometimes see atoms presented as tiny solar systems, a dense little nucleus in the center, with electrons circling around it like miniature planets. Then comes the conclusion. If most of the atom is between those objects, then most of matter must be empty. Simple, memorable, and misleading if you take the picture too literally. The solar system analogy was historically useful. It helped scientists and students visualize a central nucleus surrounded by electrons. But electrons are not tiny planets following neat classical orbits around a nucleus. Quantum mechanics gives us a fundamentally different description. Electrons are described by quantum states and probability distributions. Their behavior cannot be reduced to little balls tracing ordinary planetary paths. And that matters here. Because once you remove the cartoon picture of miniature planets flying through a vast empty room, the phrase mostly empty space stops being an explanation for why matter is solid. It becomes a starting point. This is one of those places where I think popular science explanations sometimes become too satisfied with a dramatic sentence. Atoms are mostly empty. Fine, but then what? Why does your hand stop at the table? Why does one atom resist being compressed into another? Why does matter have structure at all? Those are the questions the slogan does not answer. And there is an important distinction here. The slogan isn't necessarily the problem. The problem is pretending that the slogan is the complete physics. Reality involves quantum states, electron distributions, electromagnetic interactions, and the properties of atomic nuclei. These ingredients work together to produce the behavior we experience as ordinary matter. So when someone says, matter is basically nothing because atoms are mostly empty, you should recognize that something important has been left out. Not because the universe is secretly filled with some mysterious substance, not because empty space is hiding a magical force, but because the microscopic rules are much richer than the picture suggests. And that difference is not merely academic. It changes the entire explanation of why the chair feels solid in the first place. So if the viral explanation is incomplete, what does a better explanation look like? And why should we care about the difference? This is the kind of physics worth slowing down for. Not because the ideas need to be made complicated, but because they deserve better than a catchy sentence that leaves the important part unexplained. The goal here is simple. Take something that sounds mysterious, look at the actual mechanism underneath it, and then bring that mechanism back into the ordinary world you experience every day. Because physics becomes much more interesting when you stop memorizing what happens and start understanding why it happens. If you appreciate that kind of explanation, where difficult ideas are taken seriously but explained in plain language, stay with me through the rest of this one. There is much more hiding underneath that supposedly empty space. Now let's go down one level, from the chair you are sitting on to the microscopic structure that makes that chair possible. Now let's go down one level, from the chair you are sitting on to the microscopic structure that makes that chair possible. Start with scale. A typical atom is roughly 10 to the power of minus 10 meters across. A typical atomic nucleus is roughly 10 to the power of minus 15 meters across. That is a difference of about 100,000 in linear size. So when people say an atom is mostly empty space, they are pointing toward a real feature of atomic scale. The nucleus occupies an extraordinarily tiny region compared with the overall size of the atom. But there is an important warning. That remaining region should not be imagined as a perfectly empty little box with absolutely nothing happening inside it. To understand why, we have to separate two ideas that are often accidentally mixed together: where the mass is and where the atom's structure exists. Almost all of an ordinary atom's mass is concentrated in its nucleus. A proton has a mass of about 1.67 times 10 to the power of minus 27 kilograms. An electron has a mass of only about 9.11 times 10 to the minus 31 kilograms. So a proton is roughly 1,800 times more massive than an electron. That means the nucleus contains almost all of the atom's mass. But mass concentration does not mean the nucleus occupies almost all of the atom's volume. Those are completely different statements. Imagine a huge stadium containing a tiny but extremely heavy object at its center. Almost all the weight could be concentrated in that object, while the object still occupies almost none of the stadium's volume. That is roughly the distinction you need to keep in mind. Now we reach the part where the familiar planetary picture has to go. Electrons are not tiny planets orbiting the nucleus along neat circular tracks. In quantum mechanics, an electron is described by a quantum state. In an atom, those states are associated with orbitals, mathematical descriptions that tell us about the probability of finding the electron in different regions around the nucleus. When people draw an electron cloud, they are not showing a tiny fog made of classical material. They are visualizing the spatial structure of the electron's quantum state, and that changes the question. Instead of asking, what is between the nucleus and the electron like it would be between two little balls, we should ask, what quantum state does the electron occupy? That question sounds more abstract, but it leads us directly toward the reason atoms are stable. If electrons were simply classical charged particles orbiting a nucleus, classical electromagnetism would create a serious problem. An accelerating electric charge radiates electromagnetic energy. A classical electron orbiting a nucleus should therefore lose energy and spiral inward. But ordinary atoms do not behave that way. They have stable quantum states. The electron does not simply follow a little planetary orbit while continuously losing energy until it crashes into the nucleus. Quantum mechanics gives us a different structure altogether. Only certain allowed quantum states exist, and electrons can occupy those states without continuously radiating energy merely because they are in a stationary atomic state. This is one of the first places where our everyday intuition fails. The atom is not a miniature solar system. It is a quantum system. And once you have that picture, we can ask what happens when two atoms approach each other. This is where electromagnetism becomes impossible to ignore. The nucleus contains positively charged protons. The electrons carry negative charge. When two atoms come near one another, all of these charged components participate in electromagnetic interactions. The electron distribution of one atom interacts with the nucleus and electron distribution of the other. At certain distances and arrangements, these interactions can allow atoms to form stable molecules or solids. At other distances, pushing the atoms significantly closer can become energetically unfavorable. So when you press your hand against a table, you are not encountering a mysterious microscopic wall hidden inside the atoms. The atoms in your hand and the atoms in the table are interacting through electromagnetic forces and quantum mechanical rules. But there is another crucial ingredient. Electrons are fermions, and identical fermions obey the Pauli exclusion principle. In simple terms, identical electrons cannot all be placed into exactly the same quantum state. This does not mean there is a tiny invisible force beam shooting between your hand and the table. Pauli exclusion is a quantum mechanical constraint on the allowed states of identical fermions, and that distinction matters. It is tempting to say, Pauli exclusion is the force that makes matter solid. That is too crude. The stability and resistance of ordinary matter involve both quantum statistics and electromagnetic interactions, along with the detailed quantum structure of the atoms and the material. Pauli exclusion is one of the essential pieces, but it is not a standalone explanation for every form of solidity. Now bring all of this back to your hand. You move your hand toward a tabletop. At first, the atoms in your hand are separated from the atoms in the table. As you get closer, their electron distributions begin to overlap more strongly. The electromagnetic interactions change. The quantum states available to the electrons become constrained. Trying to force the atoms into configurations that are not energetically or quantum mechanically favorable requires energy. At the macroscopic level, your muscles provide that energy as you push. The table responds with a force on your hand. Your nervous system interprets that interaction as contact. And that is what you experience as the table being solid. Notice what did not happen. You did not hit a miniature brick wall sitting inside every atom. You did not discover that the nuclei themselves were physically touching. And you did not suddenly encounter a layer of mysterious stuff filling the supposedly empty region. Instead, enormous numbers of atoms are obeying quantum mechanics and interacting electromagnetically. The solidity you experience is an emergent property of that collective behavior. Emergent simply means that a large-scale property arises from many smaller components following underlying rules. Temperature is an example. A single molecule does not have a temperature in the everyday sense. Temperature becomes meaningful as a collective property of enormous numbers of particles. Solidity is different in its details, but the basic lesson is similar. The chair feels solid because an enormous collection of microscopic constituents behaves in a way that produces resistance to deformation and penetration at ordinary scales. And consider how enormous that collection can be. An everyday object can contain roughly 10 to the 25th to 10 to the 28th atoms, depending on its size and composition. That means the chair beneath you is not one simple microscopic structure. It is an unimaginably large collection of quantum systems interacting according to precise physical laws. The same is true of your hand. The same is true of your bones. The same is true of the phone sitting beside you. The same rules are operating everywhere. Atomic distances themselves are tiny, often measured in fractions of a nanometer. The characteristic energy differences between atomic states are commonly measured in electron volts. These numbers are useful not because you need to memorize them, but because they tell you just how far removed this world is from ordinary human scale. The speed of light, about 3 times 10 to the 8th power meters per second, is enormous on our scale. But even light travels an extremely small distance by everyday standards in the time it takes an atomic system to undergo microscopic processes. The microscopic world is not simply a miniature version of our world. It follows rules that eventually produce the world we recognize. And now we can return to the phrase that started this entire discussion: mostly empty space. As a statement about scale, it can be useful. As a complete description of reality, it is dangerously incomplete. The atom's nucleus is tiny. Most of the atom's mass is concentrated there. The electron occupies quantum states spread over the atomic scale. Electromagnetic interactions govern how charged constituents influence one another. Quantum mechanics determines which states are allowed. Pauli exclusion restricts how identical electrons can occupy those states, and the collective behavior of enormous numbers of atoms produces the familiar solidity of ordinary matter. So the strange thing is not that your hand somehow touches the solid interior of another atom. The strange thing is that contact itself is an emergent physical interaction. Your hand never needed to encounter a miniature hard sphere inside the table. The quantum structure of matter was enough. And this is where the common explanation breaks down, because if you imagine matter as mostly vacant space, the way most people behave around that fact suddenly makes very little sense. Here is where the phrase mostly empty space creates a surprisingly powerful mistake. You hear the word empty, and your brain naturally supplies the rest. Nothing is there. Nothing is happening. Nothing should stop anything else from moving through it. That is a perfectly understandable conclusion. In fact, the wording almost invites you to make it. If someone tells you that an atom is mostly empty, you naturally picture a tiny object with a huge hole inside it. And if two objects are mostly holes, why shouldn't the holes simply overlap? Why shouldn't your hand pass straight through the table? But that mental picture is the problem. The space associated with an atom is not a giant hollow cavity waiting for another object to occupy it. There are quantum states describing the electrons. There are charged particles interacting electromagnetically. There are rules governing which quantum configurations are allowed. And there is an entire structure of matter that cannot be reduced to the idea of little solid pieces separated by empty gaps. Think about your hand approaching the tabletop again. If you imagine atoms as miniature containers with nothing inside except a tiny nucleus, the situation seems absurd. Your atoms have huge spaces. The table's atoms have huge spaces. So why not simply line up the spaces and pass through? Because atoms do not behave like empty containers. Their electron states occupy the relevant atomic scale, and when atoms are brought together, those states interact and become constrained. The electromagnetic interactions between their charged constituents also change. The result is that certain configurations are energetically unfavorable or quantum mechanically unavailable. At our scale, you experience that as resistance. You call it contact. You call it hardness. You call the object solid. But underneath those familiar words is a microscopic process that your senses never directly reveal. And this is an important point. You were not foolish for imagining empty as meaning nothing. You were given an incomplete picture. The phrase sounds as though someone has already explained the mechanism. It hasn't. Mostly empty tells you something about scale. It does not tell you what the electron states are doing. It does not tell you how electromagnetic interactions behave. It does not tell you how quantum restrictions shape the allowed configurations of matter. And it certainly does not mean that ordinary objects are mostly nothing. A table is not 99-point-something% useless space with a little bit of matter sprinkled through it. It is a highly organized physical system whose microscopic constituents obey quantum rules. That distinction changes everything. Once you stop imagining the atom as a tiny hollow ball, the mystery becomes much more manageable. The real question is no longer, why don't the empty spaces let me pass through? It becomes, what configurations can matter actually occupy? And what happens when we try to force those configurations together? But there is one belief hidden underneath all of this that causes an even bigger misunderstanding. And once you separate that belief from the actual physics, the entire picture becomes clearer. There is one picture of the atom that almost everyone has seen. A tiny nucleus sits in the center. Electrons circle around it. The whole thing looks like a miniature solar system, with the nucleus playing the role of the sun and electrons acting like tiny planets. It is a remarkably memorable image, and that is exactly why it survives. The picture has historical value. Early atomic models helped scientists build increasingly accurate ideas about the structure of matter, and the planetary analogy can still provide a rough first step for someone encountering atomic physics for the first time. But there is a problem when the analogy becomes the explanation. Electrons are not tiny planets traveling around the nucleus on fixed classical tracks. That is not what an electron inside an atom is doing. Modern quantum mechanics gives us a different description. An electron in an atom occupies a quantum state. Instead of assigning it a precise little orbit around the nucleus, quantum mechanics gives us information about the probability of finding the electron in different regions of space. That is where the familiar word orbital comes in. And orbital is an unfortunate word if you hear it as orbit. An orbital is not a racetrack. It is a mathematical description of an allowed quantum state and its spatial probability distribution. When textbooks show those familiar shapes, spheres, lobes, rings, and other patterns, they are visualizing the mathematical structure of those quantum states. They are not showing tiny clouds of classical material floating around the nucleus. This distinction may sound subtle, but it changes the entire mental picture. In the planetary model, you can imagine asking, where is the electron right now on its orbit? In quantum mechanics, that question cannot always be answered in the classical way you expect. The theory gives probabilities and quantum states rather than a simple miniature planetary trajectory. And this is not merely a philosophical preference. Quantum mechanics was developed precisely because classical ideas could not adequately describe atomic-scale phenomena. Today, organizations such as NIST and CERN, along with physics departments and research institutions around the world, work with theories and experiments built on this quantum description of matter. The important lesson is not that the old picture was stupid. It wasn't. It was a useful stepping stone. The mistake is carrying the stepping stone across the entire river and treating it as the destination. So replace the picture. Do not imagine a tiny solar system. Imagine a quantum system with a compact nucleus surrounded by electrons occupying allowed quantum states whose spatial distributions extend across the scale of the atom. Now the phrase, mostly empty space, becomes more precise. The nucleus is extremely small compared with the overall atomic scale. But the region around it is not simply a featureless void. It is where the atom's quantum structure is described. And once you stop imagining the atom as a tiny solar system, the original mystery finally becomes much easier to answer. So what should you actually picture when you hear the words mostly empty space? Now you can test the better model yourself. You do not need a microscope, a laboratory, or any equipment. Give yourself about 90 seconds. Step 1. Picture the nucleus. For roughly 30 seconds, imagine an atom at its ordinary scale. Then shrink the nucleus dramatically in your mind. Remember the basic relationship. The atom is around 10 to the power of minus 10 meters across, while the nucleus is around 10 to the power of minus 15 meters across. The nucleus is incredibly small compared with the atom, but do not fill the remaining space with the word nothing. Step 2. Replace the planetary orbit. For the next 30 seconds, stop imagining electrons as tiny planets following circular tracks. Instead, picture an electron in an allowed quantum state, described by a probability distribution extending across the atomic scale. You are not imagining a fuzzy ball of material. You are imagining the mathematical structure that tells you where the electron can be found. Step 3. Bring two atoms together. For the final 30 seconds, imagine two atoms approaching. Do not picture two hollow containers bumping into each other. Picture their quantum states and charged constituents interacting. As the atoms are forced into closer configurations, electromagnetic interactions and quantum restrictions determine what arrangements are energetically and physically possible. Now apply that model to your own body. Place your hand against a table. Stand on the floor. Sit in a chair. In each case, remember what is actually happening. You are not discovering a miniature solid wall hidden inside the atoms. You are experiencing the large-scale consequence of enormous numbers of particles obeying quantum rules and interacting electromagnetically. And that is the real payoff. The conclusion is not that matter is nothing. It is almost the opposite. Matter is structured, dynamic, and governed by precise rules. Rules that produce the solidity your senses experience every moment. Now go back to the exact moment where we began. The moment your feet touched the floor and the ordinary world felt completely solid. Your feet are still on the floor. The chair is still supporting you. The table is still stopping your hand. Nothing about those objects has changed, but your understanding has. Every moment of contact is the large-scale result of microscopic rules operating beneath your senses, quantum states, electromagnetic interactions, and the collective behavior of enormous numbers of atoms. And this happens every morning, every step, every time you sit down, every time your hand touches something, thousands upon thousands of times across your lifetime. The ordinary world was never simple. You were simply looking at it from the outside. And once you learn to look at ordinary reality this way, there are many more familiar things that stop looking ordinary. If you enjoy explanations that go beneath the slogan and reveal the actual mechanism, there is much more to explore here. No unnecessary mysticism. No pretending complicated physics is simple. Just careful science explained clearly. Because sometimes, the most surprising discoveries are hiding inside the ordinary objects you touch every day.